BC extreme events. So this is the first of one of those 4 sessions, BC Extreme Events 1, Atmospheric Rivers and Associated Impacts. And I just wanted to call people's attention to the other 3 sessions that are happening. Part 2 is going to happen today at 12:55 p.m. There's a session about heat waves and at 2:55. Tomorrow, part 3 will happen at 8, the same time tomorrow. And tomorrow there's also a panel discussion happening responding to BC extreme events that looks really interesting, also at 12:55. All of those times quoted are in Central Standard Time, so note the conversion to your local time zone. So a few just brief housekeeping notes. I'll introduce the session speakers, and then the presenters will take over their presentations. I'll give people a 1-minute ping in the chat just when they're getting close to that 12-minute mark. We'll try to stick to the 12-minute mark for the 15-minute talks and then 3 minutes of questions. I did want to note we did have a bit of a change to the schedule, or a bit of a hiccup. So what we are going to do is we are going to bypass that 10-minute break, and we're going to go directly from Kent Moore's talk to Tim Ashman's talk. So I do note, if you do need a break or need to grab a coffee or water, please do so, because we're going to try to keep going on. As I mentioned, that was just a bit of a hiccup in terms of the scheduling and the length of talks. So hopefully that works. I do note that there's not a poster session for this. There is just the 4 sessions, the 4 oral sessions. So hopefully that works. Okay, great. Well, thank you everybody for being here today. And I do also want to acknowledge that I'm speaking to you from the traditional territories of the Ktunaxa peoples today. Okay, so let's get into it. A really exciting session for today. So let's start. We're going to start today with Bobby Sekhan. Bobby is a warning preparedness meteorologist with Environment and Climate Change Canada. And with that, take it away, Bobby.
All right, thanks a lot, Ashley. Let me just share my screen and let's get started. Okay. Good morning, everyone. My name is Bobby Sekhan, like Ashley mentioned. Today, I'm going to be presenting to you about the antecedent conditions and impacts from the atmospheric rivers over southwestern BC in November 2021. And I just want to recognize that the climate stats that I used in my presentation came from Giselle Bramwell, a regional climatologist. She's always so helpful. I also want to just quickly acknowledge that today I'm coming to you from the traditional and unceded territory of the Coast Salish people, including the Katzie, Kwantlen, and Semiahmoo First Nations, and I'm very grateful to live, work, and play in these great lands. I also want to just take a look back and recognize the catastrophic events that happened in the middle of November 2021. Lives were lost, lots of property damage, infrastructure damage. It was quite a terrible time. And I just want to thank everyone involved in the emergency management community that helped with the not only the response, but the recovery effort too, and especially those first responders who were out there trying to save people and help people. And just want to acknowledge that, and our hearts go out to all the people that were affected by this destruction. Today, I'm going to be basically giving an overview of the atmospheric river events in November 2021 and the associated impacts. Basically, I'm going to give the overview, and then subsequent talks are going to actually get into more of the details. So I'm just going to set it up in a sense, talking about antecedent conditions, the meteorological setup, climatological analysis, and then the partnerships that we leaned on as well. All right, let's get started here. So the story starts really back in September. This event was months in the making. Basically, on the right side, you can see a daily precipitation chart from Abbotsford there, and you see from about the middle of September onwards, we saw pretty consistent precipitation with several atmospheric rivers coming through. And so, you know, this was not just the mid-November event, it was actually months in making. And on the left side, you actually see the precipitation percentiles, and the purple all over southwestern BC is painted as 98th to 100th percentile. So you can see just how much rain that was, and places like Abbotsford received 885 millimeters. That's that's almost double their precipitation in a normal fall. So that was quite exceptional. Another factor involved here was early season snow. This tweet from our weather office on the left side kind of shows it pretty descriptively. November 10th, they tweeted saying that winter driving conditions began weeks ago. So there was snow on the mountains weeks prior to this mid-November event. On the right side, you see actually a image from the Avalanche Canada blog, which shows on the 7th of November that there was a system that came through, freezing levels down to 900 meters, meaning there were some flurries on the higher elevations. So yeah, that proved to be a factor later on as far as the early season snow on the mountains. Now, what were the forecast challenges here? Like I mentioned, the antecedent conditions, we knew it was wet. We knew it was consistently wet. Now, when we would start to see impacts, that was a bit of a challenge. The exact orientation of the atmospheric river and how much precipitation there might be, the alignment and the amount of lift and the convergence, it all adds to how much precipitation there could be. But it's all obviously hard to predict down to the exact orientation. Snow melt and how much snow would melt and how much of this rain on snow would be a factor with the high freezing levels. That was another challenge. Also, going back to past wildfire years, the burn scar areas, places that have lost trees and the soil is hydrophobic, does not absorb moisture, and is prone to debris flows and mudslides. How would that be affected as this atmospheric river pushed deep into the mountains? Looking at the total precipitable water animation here, and you can see in green, we've highlighted that the moisture is coming up from Hawaii pretty much, so that warm, moist, tropical air. And you see in the bottom right picture, the orientation of the Fraser Valley. And you can see as this animation goes on, how that plume really aligned into the Fraser Valley, pumping that moisture, converging through the valley, getting deep into the mountains, lots of lift, and that was a big factor here in terms of all the impacts we saw, not only in the Fraser Valley, but even on the other side of the Cascades. Heavy precipitation. Obviously, this event had copious amounts of precipitation, and on the left side, you see a chart where, mind you, this is a combination of model, gauge, and radar data, but it paints a good picture in terms of the extreme rainfall that we saw. Over 340 millimeters, as it can be seen on this chart, and we have reports of around 300 millimeters in some places. So obviously kind of the higher terrain into the mountains, heaviest precipitation in those upslope areas, but even down into the Fraser Valley, absolutely exceptional amounts of precipitation. And on the right side, you see a radar image, which actually is towards the end of the event, just in the afternoon of November 15th, a convective band of showers came through, and that may have played a factor in just just adding to the destructive effects. Now, I'm talking about precipitation numbers. This graph by Giselle shows things really well, actually. These purple dots are representing all the areas that got about 100-year return periods on their precipitation from the 13th to the 15th of November 2021. And you can see that stretches from southern Vancouver Island right into the Fraser Valley as well. If you were to do a line of best fit here, you can kind of see it aligning right on along the Fraser Valley, which is no coincidence for sure, as we mentioned a couple slides ago. In terms of precipitation amounts, Hope was really up there in terms of 295 millimeters, Agassiz and Cultus Lake 228, even southern Vancouver Island meant chosen over 200 millimeters. So this kind of shows these top 5 locations that I found, but yeah, it's almost a month's worth of rain in just a few day period there. Now let's get into some of the impacts. Obviously, we had lots of flooding and landslides over southwestern BC. The map on the right side shows that quite well, stretching everywhere from Vancouver Island right into the southwestern interior and the Nicola Valley and the Similkameen Valley. It was nearly a month's worth of rain fell in just 3 days. And, that included getting into places that were already wet from antecedent conditions, burn scar areas, and it set off all these impacts. We had $450 million in insured damages as reported by IBC, and some say the damages could be as high as $7.5 billion US. It was an absolutely catastrophic event. We saw fatalities. 5 people lost their lives, unfortunately. Evacuations. The city of Merritt, 7,000 people evacuated due to the wastewater facility. We saw agriculture destruction, crops everywhere from blueberry to saffron, absolutely destroyed in the CMOS Prairie area. We had animal deaths. Over 1 million animals lost their lives during these flooding events. And severed transportation routes. Vancouver, having one of the biggest ports in the country, was cut off from the rest of Canada because every highway out of the lower mainland was shut down at one point due to these landslides and flooding and washouts. And of course, power outages, which Tim will be, I'm sure, touching on later as well. Taking a look at some of the pictures of the impacts, obviously very devastating events and can be hard to look at for sure, but we see in the top left, the Abbotsford flooding in the CMOS Prairie, the former CMOS Lake area there, and 628,000 poultry lost there, 420 dairy cattle, and 12,000 hogs all died in this historic flooding. Also, 110 beehives were destroyed, which we know how important bees are to everywhere, really. We also saw basically the Nooksack River overflowing its banks, which led into the Sumas and caused all this flooding as well in the Sumas Prairie area. So quite unfortunate. We see the destruction on the Coquihalla in the top right. Obviously a lot of transportation routes affected, but the Coquihalla being such a major route, it just snapped in places, which was really quite terrible. In the bottom left, you see trapped motorists between 2 mudslides, and they had to be airlifted by helicopter, which is absolutely incredible. And in the bottom right, talking about southern Vancouver Island as well, 150 millimeters of rain between the 14th and 15th of November, and that caused flooding and the shutdown of the Malahide Highway as well. And other parts of Vancouver Island, like Shawnigan Lake, Cowichan, and Saanich, they all saw flooding too. Interior as well, it was not just a coastal event. The moisture really pumped into the interior, and we saw lots of impacts there too. On the top left, we see Highway 8 near Spence's Bridge, a road washout where a large section of the Highway 8 actually fell right into the Nicola River. And then we also saw the Merritt flooding, like I mentioned, the cold water overflowing its banks, the wastewater facility, filling, and the evacuation of 7,000 people there. Princeton had similar flooding in the bottom left there. Saw this Tulameen and the Similkameen rivers overflow their banks. And lastly, I mentioned in the bottom right, there's that infrastructure damage there near the Shakin First Nation Reserve. Now, partnerships were something that were so important to us and have been important to us for years. And people on our team have been making these partnerships with like-minded individuals from all these organizations over the past several years, and those relationships really came into play. Not only were we collaborating internally in Environment Canada between the sciences, the operational, the services, our modeling experts in Montreal, but externally as well, working closely with EMBC, River Forecast Center, the media, the health authorities. This network of partnerships that was built over the years really came into play during this event, so that we could understand what was happening, exchange information, have effective communication, collaboration, and get good messaging out to the public and to first responders to help keep everyone safe. And these partnerships are invaluable to us. Now, looking forward, the climate is changing. We know that. And if 2021 has taught us anything between the heat and the wildfires and the flooding, that we need to be prepared for more extreme weather events. We need to continue to grow our working relationships to enhance collaboration and communication. These are the relationships that helped during that unfortunate time in November, and we'll need those relationships moving forward too. All this in an effort to spread the message of preparedness to Canadians, making sure people are ready for extreme weather, they know what to do, and they're preparing well in advance, not just during events. So that's all from me. Again, my name's Bobby Seiko, and if there's a couple minutes for questions, I'd be happy to take them.
Great. Thank you so much, Bobby. So we'll keep it maybe to one question to keep us a bit more in time. So Ruping had one, Ruping Mo from Environment and Climate Change Canada. Excellent presentation. Could you comment how the antecedent conditions were taken into account when the operational forecasters were dealing with the mid-November AR?
Yeah, definitely. So a big part of our services team here in Environment Canada is to share information with our operational meteorologists. And of course, our operational meteorologists were well aware of antecedent conditions. You know, they had been quite busy since mid-November as well with dealing with multiple atmospheric rivers. And so, you know, it's certainly something everyone was aware of the sensitivity. Now, again, one of the forecast challenges was just exactly what kind of impacts can we expect from this, and that's something that's still developing, something that we're still learning, developing tools for developing expertise in. And so yeah, we're going to be hoping to get a better idea of that in the future.
Great. Thank you so much, Bobby. That was a great answer and a great presentation. So with that, we will go on to Kent Moore. So Dr. Moore is a professor in the Department of Chemical and Physical Sciences at the University of Toronto. And his presentation today is on climate change, atmospheric rivers, and the November 14th, 15th, 2021 Pacific Northwest extreme rainfall event. So take it away, Dr. Moore.
Thank you. And thanks, Bobby, for setting this up. So I'll kind of skip a lot of the background because obviously it's gone over, but I want to talk about this event. And you know, just as Bobby mentioned, I think some of the images are just really breathtaking as to the level of devastation. This is a helicopter landing outside of Agassiz to rescue some people who are trapped. Here's a picture from the helicopter itself, just seeing the number of cars that have been sort of impacted by the washout there. And again, this is covered worldwide, you know, coverage. This is from the Washington Post. First fires, now floods, British Columbia and Washington State reeling from this atmospheric river. As Bobby mentioned, there was widespread flooding and landslides. You know, there are thousands of individuals were impacted, $500 million in insured damages, probably a lot more in uninsured damages, and Axion Insurance has estimated $2 billion in economic loss. And again, you know, roads and a lot of the transportation corridors through the area were totally devastated by this event. So as we all know, an atmospheric river was responsible for this event. I like this image. This is an image from the SMOMI satellite, their day-night band, which essentially allows one to see at night. And here you can see this sort of band of kind of clouds moving up into the West Coast. This is the Saddle region here. It's the Vancouver region here. And so here's this sort of, you know, river of moisture coming up from the subtropics coming into the Pacific Northwest. This is a nice schematic, although I think there's some issues with some of the topography, but essentially it shows you this idea that one has these rivers of moisture coming up, and then the impact with topography leading to intense precipitation in the region. There's been a lot of work looking at sort of impacts of atmospheric rivers on BC and the Pacific Northwest. Mostly I'm going to talk about studies that have been used, the CMOS model results. So this is a study which predicted that the landfalling termini of atmospheric rivers that impact BC would move northwards in the next century. This is a study that had essentially the opposite result. Essentially here, this study found there was no change in the structure or evolution of atmospheric rivers that impact the Pacific Northwest in a warming climate. So there's some disagreement as to what's going to happen moving forward. There is some evidence that the water vapor transport coming into the region is going to increase over time. And this one had an exceedance frequency of the 99th percentile, water vapor transport would quadruple by the end of the 21st century under, of course, the most extreme emission scenario. And this is a study that showed the influence of atmospheric rivers would result in a quadrupling of the cold season extreme rainfall frequency again in the next century. So there's lots of evidence, I think, that in this changing climate, we're going to see changes in the atmospheric rivers, and of course that will then impact. But whether we've seen these changes or not, I think is still an open question. Hopefully I can provide some evidence for that. So in this talk, I want to do a variety of things. I want to use observations and reanalysis products to just document essentially the evolution of this extreme event. I also want to document the changing nature of atmospheric rivers. And then what I'll show essentially, and I think Bobby alluded to this, is that there's been a northward shift in the axes of these rivers. And what that does essentially is that right now, most of the atmospheric rivers come in essentially from the southwest. And so there's this barrier. The Olympic Peninsula essentially rains out some of the moisture before it can get into the kind of region of interest. And what's happened, as I'll show over time, and also for this event, this river sort of entered more along this path here. And so some of the sort of topography that essentially rains out some of this moisture wasn't able to do that. And so that may be why, in fact, this river was caused so much precipitation. So a bunch of the techniques that I'll use daily precip at Hope, which goes back to 1938. I'll use various hydrometeorological fields from the era 5 and its back extension, which goes back now to 1950 at a resolution of 25 kilometers. I'll also use precipitation from the operational analyses from the ECMWF, which is available at 9 kilometers. The reason why I want to do this is that era 5 in this operational model essentially have the same physics in them, same data assimilation system, et cetera. And so really what this does is it allows you to control for model resolution. This one essentially is being 9, this one being 25. So one can essentially, without worrying about how the physics changes from model to model, one can just see the effect that an increased resolution has. I'll also use precipitation from the Canadian precipitation analysis, which is a blend of a forecast model and also observations, including weather radar. That's available at a 10-kilometer resolution back to 2002. And then there's a higher resolution version available at 2.5 kilometers recently. And again, here we have exactly the same, if you like, analysis system, but different resolution. So again, one can control for the impact that resolution has. So what I'll do is I'll use a variety of these precipitation data sets to document the spatial variability associated with this event. I'll use trend analysis to look at how precipitation is changing over time. And I'll make use of a significance test that takes into account a lot of geophysical time series have temporal autocorrelation to them. They're red noise, if you like, and that reduces the degrees of freedom. If you don't take this into account, one can overestimate the significance of your results. Just for your interest's sake, in this case here, there's about a 20% reduction in the degrees of freedom in the precipitation data sets. I'll also use the era 5 precipitation time series to identify extreme events. I'll just use the 99th percentile as a cutoff. There's about 20 events over the period from 1950 onwards. And then I'll look essentially, use composites then to see what the structure of these rivers are that are associated with extreme events are and how they're changing over time. And then finally, I'll use the era 5 fields again to do a trend analysis, but now spatially rather than just at a point. And again, using the same methodology. So this is a time series of the daily precipitation at Hope. So again, on the 15th, I think on the 15th, there was essentially over 180 millimeters of precipitation. This is the mean for Hope over the period 1938 to 2021. This is the 95th percentile. This is the 99th percentile. So this is clearly an extreme event. In fact, it was the wettest day on record in this data set. Looking spatially, this is the precipitation on the 15th of November. And I'm showing you the precipitation from era 5, from this operational version of the ECMWF model, from the 10-kilometer kappa, and then from the 2.5-kilometer kappa data. And so you can see that generally, all of these models pick up essentially heavy precipitation in this region. Clearly, as you go to higher spatial resolution, one gets higher precipitation values. And you can see that, again, probably from the 9-kilometer operational model onwards, one can see there's two regions of heavy precipitation, one essentially in the Olympic Peninsula, and then one in the sort of southern BC, northern Washington State region here. And I'll be using this red polygon here. I'll be averaging a lot of data over this region just to get a sense of what's happening in this area. Here's an example of that. So what I've done now is I've averaged over that polygon. This is precipitation during November from ERA 5, again, 25 kilometers. The operational model at 9 kilometers, the kappa analysis at 10 kilometers, and then the high resolution kappa analysis at 3.5 kilometers. And again, I'm showing you the mean. Again, this is from these various models, the 95th and the 99th percentile value. And again, you can see all the models pick up the heaviest precipitation on the 14th and the 15th. As you go to higher and higher spatial resolution, one gets essentially higher precipitation values. So again, the models are able to capture the extreme nature, but of course there's a resolution effect, mostly probably because of the extreme topography in the region. And so at 3.5 kilometers, one gets significantly more precipitation than you do at 25 kilometers. We should, of course, try to validate our models against observations. And this is the scatter plot of the HOPE daily precipitation and the ERA 5 daily precipitation interpolated to the HOPE site. And one can see that the fit's not fantastic. One obviously sees there's a positive correlation here, but again, the variance is quite low. There's large RMS errors and large bias errors. And of course, this is a classical problem. There's a real difficulty in reconciling point precipitation observations with models, especially in regions of complex topography. There's two things that can be going on. The point observations may not be representative of what's happening in the larger area. And of course, a model may have biases. So I don't think we should expect too much of ERA 5 precipitation at HOPE itself, but hopefully if we look at in a region, one can get a better sense of that. And this is now what I've done now is I've now taken in the area of interest, I've taken the kappa daily precipitation. This is the 10-kilometer product, and I'm doing a scatter plot with the ERA 5 daily product. And again, you can see here the fit's much better. Again, the slope is close to 1, the R value is quite high, the RMS error is quite low, and there's a bias error. So again, if you look in a regional context, I think all of these models are able to capture the precipitation in the region. So now I want to skip forward and look at just the monthly mean statistics. And so what I'm showing here is this is the observations at HOPE. This is the monthly mean precipitation during November, again, starting in 1938 to 2021. And this is the daily precipitation at HOPE. Again, this starts in 1950 and goes to 2021. I put the slopes, the trends on both of these ones. Both have positive trends, again, with high significance. Again, this takes into account the temporal autocorrelation of the time series. And you can see, especially if you look at the observations, for the month of November, 2021 wasn't the most extreme event. The most extreme month was actually 1990 in here, but it was the second highest monthly mean precipitation at HOPE. And so one has these positive trends. And again, so of course, one of the worries with ERA 5 is we're going back to 1950. There's obviously very little data, such as precipitation related data being assimilated back in the 1950s. If you look at the ensemble version of ERA 5, which has 10 ensemble members, and you just look at the sort of uncertainty in the daily precipitation values, there's a large uncertainty at the beginning part of the record. But even in the ensemble version, which takes into account the uncertainty, there still is a statistically significant trend in the data. And so you just look at HOPE, so they're almost getting 0.6 millimeters per decade is the trend. So since the 1930s, monthly mean precipitations at HOPE are now about 40% higher than they were back in the 1930s. And now I want to jump and look at the structure of this atmospheric river that impacted the region in November 14th and 15th. So what I'm showing you here is a bunch of times. They all have exactly the same field. So the contouring is the sea level pressure. The vectors are the water vapor vertically integrated water vapor transport, and the shading is the magnitude of the vertically integrated transport. And so you can see the river approaching on the 13th, again on the, and then by the 14th, it had started to sort of impact the Pacific Northwest. Here it is at 12Z on the 14th, 12Z on the 15th, and then 12Z on the 16th. And so what's actually interesting about this particular event is that most atmospheric rivers are associated with a region of low pressure. And you can see there is a region of low pressure up here off of, say, Haida Gwaii with some sort of trough coming down. But there's this region of high pressure to the south. And this is quite unusual for atmospheric rivers having this region of high pressure. And as a result, you can see that this atmospheric river, back up here, that this atmospheric river had a sort of anticyclonic curvature to it. And that was associated with this region of high pressure to the south. And so as a result, this atmospheric river hit the region sort of with a more perpendicular orientation. Typically, as we'll see in a minute, the atmospheric rivers have a cyclonic curvature and they come in from the southwest. And that allows them to sort of interact with the topography of the Olympic Peninsula first before hitting the region of interest. This one had this anticyclonic curvature, and so it hit the region sort of more perpendicular, if you like. And I think that, as Bobby mentioned as well, I think this had an impact on the extreme nature of the precipitation in this region here. Now I want to jump to looking sort of at a composite atmospheric river and also the change that are happening over time. So what I've done here is, again, I've taken these 99th percentile precipitation events in this region, and I've done a composite. But what I've done, first of all, here is just focus on the first half of the record. So these are the composites of the extreme precipitation events over the period 1950 to 1986. And I think there were 10 events in this composite. And you can see here now how one has this sort of, again, this sort of, meridional dipole, high pressure to the south, but very essentially much stronger low pressure to the north. And so you can see this sort of, if you like, this cyclonic curvature to the typical composite atmospheric river. And so it enters the region, if you like, essentially from the southwest. And that allows it to interact, first of all, with the topography of the Olympic Peninsula before getting into the region of interest. And as we'll see, more recently, the rivers have shifted northwards, as the one in 2021 did. Here's the precipitation. I think it's kind of interesting. Look at the precipitation. So clearly you see two bands of precipitation, one associated with the essentially the coastal topography, and another band of heavier precipitation more inland, which is associated with, again, with topography in this region here. What's interesting, of course, if you look over the ocean, there's clearly, you know, high precipitation associated with these events, but there's this really, really sharp boundary to the south, right? And this essentially is the southern limit of the atmospheric river, okay? So this is a typical, if you like, atmospheric river causing an extreme precipitation event in this region here, again, back over the period 1950 to 1986. What I now want to show you is the difference in the composites between that first period and the more recent period, okay? And here again is this difference, if you look at it in terms of the integrated moisture transport. So you can see how there's been this shift northwards, right? So now the rivers are now essentially, there's heavier moisture transport in the northern part, and there's a reduction in the moisture transport in the south. So this is evidence, I think, that these atmospheric rivers are shifting northwards over time. If you look at the precipitation difference, again, one sees this dipole here, heavier precipitation, essentially, in this region of interest, and a reduction in precipitation along to the south, along the coast going down towards California, okay? So again, I think this is evidence that these rivers have shifted northwards over time. And of course, that will also, as we'll see, cause them to now enter the region, again, sort of in a more perpendicular direction rather than previous case, which is from essentially from the southwest. and that essentially removes this topographic barrier to the flow. Okay. This is the integrated water vapor transport and precipitation. One can also see this in the total column water vapor. So again, this is now the composite over the entire period of time. And again, you can see this, these atmospheric rivers are associated with these essentially high transport of water vapor up into the region. If you look at the difference between the period 1950, 1986 and the more recent period, again, one sees the same kind of dipole with a increase in column water vapor to the north, a decrease to the south. And again, I would suggest this is evidence that these rivers, in fact, these are rivers that cause extreme precipitation in this region of interest are in fact shifting northwards over time. Okay, so again, so these changes are all consistent with what we see in the water vapor transport and in the precipitation. One final one here. This is now looking at the divergence of the integrated water vapor transport. Again, this is the composite over the entire period of time. And of course, one sees strong negative values. So negative values mean convergence. And of course, convergence would map into precipitation. And so you can see, again, the effect that topography has. There's these sort of two bands where there's strong convergence, one along essentially the coast of Vancouver Island and into the Olympic Peninsula, and another region of strong convergence associated with coastal mountains. And of course, this is the region that we're interested in here. If one looks at the difference, again, between the first half of the record and the second half of the record, one again sees this dipole with now one has essentially reduced convergence, if you like, to the south. So this would map into less precipitation in this region. And then in the north, both along Vancouver Island and into the region of interest, one sees enhanced convergence. So again, one has then more precipitation falling in this region here. Okay, so one sees there's all these meridional dipoles with essentially associated with a northward movement of the water vapor transport, northward movement of total column water vapor, and also enhanced precipitation to the north and a reduction in precipitation to the south. So one final thing to look at are just trends. And we looked at trends in this sort of when we average over this particular box here. Now I want to look at trends over the whole region. So these are now looking at the trend in November daily precipitation. This is from ERA 5. Positive values mean there's an increase in precipitation over time. Negative values, a decrease. The stippling are in regions where the trend is significant at the 10th percentile level, not super significant, but one can again see this region essentially extending from the interior BC over into the northern part of the Pacific Ocean off of Vancouver Island. Again, positive precipitation in this region, positive trend in precipitation, and then to the south, negative trend in precipitation. So we're getting less precipitation in November in this region, more precipitation in this region. Again, and that's again consistent with what we see when we do the composites over the extreme events. One final one, this is now the trend in the magnitude of the integrated water vapor transport. Again, one sees positive trends in this northern region and then negative trends at least offshore, especially here, okay? So again, this is meridional dipole. So again, we're seeing more, if you like, water vapor transport into this region over time. So just to conclude then, so in mid-November 2020, we had this extreme precipitation event that was most intense in southern BC and northern Washington state. Observations at Hope, as well as a variety of data sets, show that this was really an extreme event, exceeding the 99th percentile level. In fact, it was much higher than that, probably 99.9 percentile value. The Hope station data, as well as the ERA 5, both have positive trends in monthly mean precipitation during November. And so this means if you look at the Hope data, there's been an increase of about 40% in the monthly mean precipitation since the 1930s. So again, this extreme rainfall event was associated with this atmospheric river that transported moisture from the subtropics into the Pacific Northwest. Unlike the majority of these rivers that are associated with extratropical cyclones, this river was most strongly influenced by a subtropical region of high pressure. And as a result, the curvature of this river was anticyclonic, and so it made landfall more perpendicular to the coast of Vancouver Island than is usual. And this is a sort of schematic of sort of typical case. So the typical case, these atmospheric rivers have cyclonic curvature, and they kind of enter the region in this direction here. So first of all, they got to interact with the topography of the Cascades before they get into the coast region here. The one in 2021 sort of had a more perpendicular orientation to it. And so that allowed it to bypass some of this topography here. And so therefore there was less rain out, and there was more like water vapor available to rain out once it hit the coast topography in here. If you look over time, at least at these extreme events, the rivers associated with extreme precipitation, they also have this northward shift. And again, that helps bypass the Olympic Peninsula. And I think that's one of the reasons why we're getting heavier rainfall events in this region recently. And what's interesting is, of course, there have been greenhouse-induced observations of a northward expansion of the Hadley circulation. And that also results in northward migration of the jet stream. And there's evidence that these atmospheric rivers are sort of coupled into the location of the jet stream. And so we may be seeing essentially a impact of greenhouse gas, in increasing concentration of greenhouse gases, and that they're expanding the region under the influence of the Hadley circulation. That's northward moving the jet streams, and it's also dragging the atmospheric rivers along with them. So thank you very much, and I'm happy to answer any questions that there are.
Great. Thank you so much, Dr. Moore. That was great, but terrifying from a river forecast perspective for the coast of BC. So a couple of questions, and we do have a couple of minutes before we go on to our next speaker. The first question, just chronologically in the chat, I appreciate everybody putting that in there. The challenge of BC's topography, which makes it difficult to predict things like precipitation convergence from the amount of water vapor. Could you discuss these challenges? With a follow-up note, whether the main topographic factor is the Olympic Peninsula.
Yeah, that's a good question. And, you know, the topography is incredibly complex. What can I say? You know, and even frankly, you know, so if you go down to the, you know, this high resolution version of the Canadian precipitation analysis at 2.5 kilometers, it's probably still not capturing a lot of the variability. So it's a real challenge. One thing which is good about atmospheric rivers is that they're synoptic scale events, right? So essentially, one can probably have good confidence in the upstream characterization of the river before it hits the topography. And that's, in fact, other people have noted this, is that, you know, the hardest thing to forecast is sort of locally forced precipitation in locally complex topography. We don't have that problem here. This precipitation is being forced by these, you know, these synoptic scale rivers. And so at least we have the ability to characterize to some extent what's coming into the region. And then it's really just a matter of can we capture the interaction of the topography with that. And I think, you know, if you look at that scatter plot of ERA 5 versus Kappa at Hope, it's not doing a bad job, at least when you look at a regional perspective. So we're probably doing an okay job. What's the limit of that? I don't know. You know, the one thing good about the Kappa is that it's ingesting the radar data. Again, I think radar data in regions of complex topography also has issues. So there's probably some limit as to how well we can actually kind of resolve these features. But I think we're doing a pretty good job. Whether or not the Olympic Peninsula is the deciding factor, I think it's an interesting kind of, at least what I was kind of surprised is I could see that these rivers, and especially one in 2020, tended to have a different orientation than usual. So they're clearly bypassing this region, at least some of this region here. So is that what's doing it? I think it's an interesting hypothesis. One would have to test that, I suppose, by running some models where you take out, you know, maybe the topography of the Olympic Peninsula and see what's happening over time. But I think it's sort of at least there's a geometrical factor here at play, which I think is related to the Olympic Peninsula.
Great. Yeah. And there's a follow-up question here that relates to CAPA as well, about CAPA seeming to show systematically higher precipitation for the November 2021 event than ERA 5 or ECOA. Do you have any idea why this might be? And maybe this is kind of a connected question to that.
I think it's resolution, because if you compare ERA 5 to ECOA, they're the same essentially model, different resolutions. So obviously the 9-kilometer version is capturing more of the uplift that's, say, associated with the topography. And then if you look at the two versions of CAPA, the higher resolution version of CAPA has higher values. And again, the model's essentially the same. You know, they're only assimilating the data to higher spatial resolution. So I think it's really just the ability of, when you go to higher model resolution, to capture more of the topographic effects. That's I think what this shows. So I'm not that concerned that the CAPA is not as high as the high resolution version, because you just expect the higher resolution version to capture, you know, because again, there's a model in the background there, and that model is, you know, it's the high resolution deterministic precipitation system. So it's, you know, capturing more of that kind of interaction of the topography with the incoming moisture. So I would expect that to be the case. It just shows you, I think, that that model resolution is important in these regions of complex topography.
Yeah, great. So we're just 1 minute behind schedule, but I'm going to just follow one last question, and it's a great one. In a warming climate, the atmosphere can hold more water vapor. How would this factor affect the precipitation efficiency of ARs in the future?
That's a good question. I think, you know, notwithstanding any other changes, if you have more, you know, if you can hold more water vapor, these rivers are going to have more water vapor, and so they're going to have more precip when they eventually interact with topography. What's additional wrinkle here is it looks like there's a changing orientation to the rivers, and so even if one didn't increase the amount of water vapor in the river, I think by changing the way they interact with the topography, you're going to see higher. So it'll probably be a double whammy in a sense that and we may be seeing some of that as well, right? I mean, you know, if you go back to the total column water vapor, you know, there's an increase in total column water vapor. So we're seeing that already, but I think this geometric factor is just an added thing, which is going to boost precip, especially in regions like the Fraser River Valley.
Great. Well, thank you so much, Dr. Moore. That was really a fabulous talk. And I apologize to people whose questions we didn't get to, but we're a bit behind. We'll go to Tim Ashman. Just a note that we are going to keep going on just because of that scheduling issue. So Tim Ashman is a meteorologist at BC Hydro. And with that, I'll hand it over to Tim. And Tim, if you're talking, I think you might be on mute.
Hi, yes, just figuring things out here. Can you hear me now?
Can confirm we can hear you. Cannot
Okay.
see your screen, however.
Okay, I'll reshare my screen. Sorry about that. Screen 2, where does screen 2 go? Okay, can you, sorry about this. Just having a bit of difficulty here. Can you see my screen now? Is it the full screen version?
I can see your screen, however, I cannot see the full screen version.
Okay, just one moment. I just tested this. Okay. Sorry, just bear with me here. Okay, I'm just going to close this. And this is not working well. Sorry. What's going on? Yeah, okay, I'll do a new share. Oh, here, it's back. Okay, this should work. Sorry about that. Can
Okay,
you see the
perfect.
full screen version now?
Can confirm we can see the outline slide for your talk.
The outline slide. Okay,
Yes.
perfect. Okay, so I'm one of several contributors to this talk, and a few of us are here today. We'll be taking turns stepping through the presentation. So first of all, just some comments about the impacts to BC Hydro. There were impacts on several levels. One is in terms of our infrastructure, our transmission and distribution lines impacted by debris flows, also impacted by high winds with the November 14th, 15th atmospheric river. So that was one type of impact. The other type was on the generation side of the company, high inflows into our watersheds, and the need for us to act in a timely and responsible manner to manage that water. And today's talk will focus primarily on that, the generation side of the impacts. So going on to the outline now, Frank will take you through the hydrometeorological monitoring challenges during the event. Then I'll take over again and talk about some key watersheds, precipitation rankings of the extreme mid-November event. Also weather forecasts, inflows, and snowmelt for that same event. And then Joanna, one of our operational planning engineers, will take over and talk about operating of our generation facilities. So I'll pass it over now to Frank. Okay, well, let's see here.
Do you see the second slide? Yep.
Oh.
There we go.
I don't know if they see that.
Just confirming that we still see your outline slide.
Okay, yeah, sorry about this. I really
Go on a different screen.
Yeah, I'll have to reshare. Down. Screen sharing. Okay. Yeah. Okay, I'm gonna have to try something different here. This one, I think we were on that one, but we can't advance it. Oh, up here. Okay, yeah, I think we'll have to do it this way. Figured it out. Sorry about that.
Okay, here we go. I'd like to quickly talk about the challenges of monitoring extreme hydrometeorological events, and here specifically high precipitation and flood events. These do pose challenges at times, and first talking about precipitation monitoring, you know, as the previous presenter showed, in this area we can get very large multi-day storm totals of over 300 millimeters, and annual precipitation can be over 4,000 millimeters. With the precipitation monitoring we do to support hydro operations, we complement valley-based monitoring networks at very remote locations and high elevations, which means that the automated stations are unattended for long periods of time. The precipitation gauge of choice for us is a in-house designed, custom-made precipitation standpipe shown on the right-hand side. It is not maintenance-free, and the capacity ranges from 750 to 1,400 millimeters. So that means you have to go regularly to drain the gauges. Particularly during storm events, there are longer periods without helicopter mountain flying weather. And as this November event showed, is also helicopter availability, as many of the helicopters were drawn away for rescue operations. So that can lead to situations where during extreme events, our precipitation gauges could fill up, leaving us without real-time precipitation data. So we took 2 steps to mitigate the situation in the future. We, with the help of Northwest Hydraulic Consultants, we designed a prototype for remotely draining these standpipe gauges. On the photo on the right-hand side, you see the reservoir underneath the gauge, which contains the antifreeze. So the remote draining mechanism works through Inmarsat satellite. It drains the gauge and recharges the gauge with an antifreeze, which allows for the monitoring of solid precipitation. Secondly, we'll start testing of a maintenance-free OTT WS100 radar precipitation sensor, a disdrometer, also shown on the right-hand side. It is believed to be of lower quality. It is believed to produce lower quality precipitation data, but it would give us a redundant additional source of precipitation data during these extreme events. And the reason that we use these standpipe gauges is that we have in these areas potentially high solid precipitation intensity and amounts, so lots of snowfall. That leads to snow capping issues and either reduced data quality or a lack of precipitation data. So we've worked on a couple of measures here. We've designed standpipe gauges with a rim heater that heats the rim and melts the snow off of the rim, keeping the orifice open. And second, we designed instrumentation towers that are streamlined such that most of the snow will usually fall around it. However, in very high precipitation areas, maintenance is still required, but it improved the situation. In terms of monitoring snow equivalent during extreme precipitation events, because of the large amount of snowpack, up to 6 meters in southwestern BC, we use snow pillows. I would say they generally provide reliable data during these events, and data from our high elevation stations, like the one shown in the lower right corner, Lamont Creek Upper, was used to estimate the snowmelt during the event. Moving on to monitoring of extreme floods. Can be an extreme challenge. Monitoring a river stage, we found, is most successful with non-contact methods. So we try to install redundant radars on rivers that are of importance to us. The understanding is that the instrumentation for low flow monitoring may be lost during these events and has to be reinstalled afterwards. But it also has to be understood that particularly during very extreme events, the stage can jump by several meters over previous maxima, which means that entire stations are lost. And it is sort of a cost-benefit question, you know, how much money you put into these stations to make them proof to the most extreme events. But I think it has to be understood that in some cases we may lose our stations, and maximum stage may have to be estimated after the fact using debris, and stage may have to be modeled after the fact. In terms of discharge measurements, the experience is that cableways are critical for monitoring high stage and discharge. Particularly crude cableways are better suited than bank-operated cableways. Also, current meters are typically more robust during these events than ADCPs, and not subject to the same negative effects of sediment. In step pool morphology and in rivers, in mountain rivers, we have successfully applied salt dilution up to 100 cubic meters per second, and sometimes even higher. It depends very much on where you can inject the salt. So we are able to measure those flows. And Water Survey of Canada, one of our main service providers for hydrometric monitoring, is investigating image velocimetry from drones as an option for measuring extreme flows in some of the rivers, which once implemented will provide a very powerful tool of monitoring discharge during these extreme events.
Okay, great. Thank you, Frank. So we'll move on now and take a look at some key watersheds that BC Hydro operates in the Lower Mainland region. And on this map, you can see some of the network that Frank was describing. The circles show climate, hydrometric and snow stations. The larger gray markers are dams. The watershed boundaries are in black. There's Coquitlam, Alouette, Stave, and Wall Leach. Wall Leach being located southeast of Hope in the Cascade Range, and the other watersheds located in the Coast Range on the north side of the Lower Mainland. I'll be focusing on some specific stations when I talk about the weather forecast. One is CQM in Coquitlam Basin, another one is ALU in Alouette Basin, and also WAH in Wall Leach Basin. Another station worth noting is LCU, that's Lamont Creek Upper Snow Pillow that Frank mentioned. We'll talk about the snow pillow data during the November 14th, 15th storm as well. So in terms of precipitation rankings at these selected sites, we look here at the 48-hour maximum precipitation totals. These are derived from rolling hourly data starting from 1990, so just over 30 years of data. So we're not looking at only calendar day, but we're looking at all the possible rolling 48-hour periods, except Hope is derived from daily data. And one thing that stands out here is that the November 14th, 15th storm ranks high. It was an extreme storm. However, at our locations, in our basins, it was not the wettest on record in the past 30 years. It was 4th wettest at Alouette, 11th at Coquitlam, and Wall Leach in the Eastern Fraser Valley. It was 2nd wettest behind the November 1990 storm, which was somewhat wetter. So despite being an extreme storm, not the wettest on record as far as our locations are concerned. There is daily data shown there for Hope as well. And I realize it doesn't jive with what Bobby and Kent Moore were describing in their talks. So it's something we might want to connect with concerning the data at Hope and whether the storm in 2021 was the wettest one on record or not. The forecast timeline. So in early November, we had several cold, wet weather systems, as Bobby described. Freezing levels were about 1,000 meters, and we were accumulating snow at middle elevations across the South Coast region. We had a first primer atmospheric river on November 11th that brought moderate precipitation and some warming, but it also did bring additional snow at middle elevations. And this event was well forecast. The extreme event, November 14th, 15th, we had good lead time on this, identifying it about 5 days before the event with the potential for a stronger, narrower atmospheric river with very heavy precipitation. So our flags were raised, and in addition to our normal weekday forecast issues and decision-making processes, we activated our weekend storm support for Sunday, November 14th. And on that day, as we were updating the forecast, precipitation was trending well so far. And we expected an increase in precipitation rates later that day and into early Monday. However, in reality, the observed rates were much heavier than forecast for the Lower Mainland and Southern Vancouver Island watersheds. BC Hydro watersheds on the South Coast, including Central Vancouver Island and the Sea to Sky corridor, and those were not hit as hard as the Lower Mainland. Our forecast system, I'm not going to touch much on the details here. The main point is that we employ a large ensemble, a super ensemble, if you will, that we bias correct. We calibrate it so that we have more accurate probabilities, and the end result is a probabilistic forecast of temperature and precipitation that is available for our hydrologists to use in their inflow forecast models. So how did the forecasts verify at these select points that we've already talked about? This is showing the forecast issued on the 14th of November for the 14th and the 15th of November. And one thing that's quite apparent is that the forecast, it was under forecast, the event. The observed is shown in the solid bold blue line. So you can see at Wall Leach Basin in the Eastern Fraser Valley, the observed rates were much higher than the ensemble rates starting around midday on the 14th of November, Sunday the 14th. And those extremely high rainfall rates continued into the Monday. And the end result was 250 millimeters, which was well above the wettest trace in the ensemble at 200 millimeters. Alouette Dam, the forecast there performed better with the precipitation, though, still near the top end of the ensemble envelope. And then for Coquitlam, the forecast performed better yet. It was still wetter than the median of the ensemble shown in brown, but it was within the upper range of the ensemble envelope itself. So while we have a sophisticated ensemble system that we feel performs well, it is clearly underperformed in this event. And this brings us to some future learnings and ways that we are looking to improve the ensemble. And one thing that we're planning to do this year is at the short time horizon, we're looking to remove coarse resolution models. Longer term improvements, we're looking to incorporate more models into the ensemble, including higher resolution convection allowing models that will better resolve mesoscale terrain effects and convective banding, two features that were quite important with the November 14th, 15th event. So now on to inflows. This is a hydrograph for Alouette Basin. The top part of the plot is the hydrograph, and it's for November 11th through 17th. And it's showing hourly inflows. There are return periods shown on this plot, but these are daily return periods that are just shown for context. So you can see we had some inflow or some runoff during the November 11th primer event, but we also know that it was adding new snow to mid elevations and mountains as well. And then with the early part of the November 13th, 14th, 15th event, flows increased. They reached 2 to 5 year return periods, but also some additional snow was added to the higher elevations. And then as the atmospheric river intensified into early Monday the 15th, this almost doubled flows within a few hours. And in addition to the heavier precipitation rates, a large contribution was from rain on snow melt. This is a look at the snow pillow data. You can see the snow accumulating early in the month of November. I should point out this is for Lamont Creek. That's in the upper Stave Basin, that site that I pointed out on the map earlier. So we continue to accumulate snow in the middle elevations during that first primer event. And during the extreme event, some additional snow was added early in the event, and then some was melted off on Sunday the 14th, 20 millimeters was melted off, and then a very large amount of snow melted off early on the 15th, 50 millimeters. So there was a total of 70 millimeters of snow melt that was added to the runoff that was already occurring due to rainfall. Rain on snow is very difficult to forecast. Model physics usually underestimate the magnitude of it, and it requires the hydrologists to manually intervene and influence their models and how they treat rain on snow. So lastly, about inflows here, these are the return periods. I want to focus on the 2-day return periods. You can see they were very high, around 100-year return periods for Wall-Leach Basin and 80-year return periods for Alouette Basin. So despite the fact that in our basins, the precipitation data was not the wettest on record over the past 30 years, the event, due to the antecedent conditions that Bobby described and also the rain on snow, in addition to the rainfall runoff, made for a very extreme event in terms of inflows and rainfall runoff into our reservoirs. So on that note, I'll pass it over now to Joanna to talk about the generation side.
There. Yeah, so I'll just talk a little bit about how we operated with this high inflow event on the Lower Mainland system. So to manage high inflows, we have a number of ways we do that. The first is storage in the reservoir. We may divert into other reservoirs. So in the Lower Mainland, that would be from the Coquitlam Basin to the Lake Bunsen and Alouette to the Stave Basin. And we can also release from the dam to the downstream waterway, which could be either through generation through our turbines, through low-level outlet gates at the dam, spillway gates at the dam, or free crest weir. So the bottom left photo here is just showing our spillway release facilities at the Alouette Dam, where we have a spillway gate and a free crest weir, and then a low-level outlet gate right at the bottom, which is just there to discharge our minimum fish flow requirements. And on the right-hand photo, it shows our diversion tunnel into Stave Lake Reservoir, where there's the Alouette powerhouse as well as a bypass adit tunnel, which can just discharge straight to Stave Lake. So our weather and inflow forecasters provide us with a probabilistic inflow forecast based on those ensemble forecast numbers. And we put that into our operational models to get an idea of where our reservoir levels and our dam outflows can reach. This helps with our planning. It lets us know based on timing when we might need to have operators out at our dams to perform things like opening the spillway gate. So on the left here, we're showing reservoir levels at Alouette with the forecast that was given on November 14th. And this dashed gray line shows an action that we need to take based on our Water Act order requirements to open the spillway gate. Our spillway gate is manually operated. So this is really helpful in letting us know the timing that we might need crews to be out there to perform the spillway gate opening, as well as finding out what our potential dam releases might be. So at Alouette, the South Alouette River runs through the city of Maple Ridge. There are concerns with potential flooding when our releases are above 42.5 cubic meters per second. And that's with contribution of local inflows, this may exceed bankful conditions at the South Alouette River. So this kind of information helps us plan with downstream stakeholders in any potential impacts that our dam operations may have. Our real-time operators who operate the system 24/7, they monitor inflows and reservoir levels as they're coming in. So this is a screenshot from Monday, November 15th at 2 p.m. And what they're doing here is calibrating the inflows that they're seeing based on a mass balance equation at the dam. Forecasted inflows are used in going forward, and our 24/7 operators may adjust these inflows based on what they're seeing from the calibrated inflows in the last hours, or they might ask the weather and inflow forecasters for additional support to understand how it's going to impact our operations. From this, we can get information about things like how much we're going to release from the dam and communicate that to downstream stakeholders for their emergency planning. This is an image of the event at Alouette from November 13th to November 17th. And although our dams are not designed to be built for flood protection, but for electricity generation, our operations can mitigate some of the downstream flows depending on the event and the system conditions. In this event, you can see the peak hourly inflows at Alouette reached 680 cubic meters per second, and our peak outflow of the dam was about 80 cubic meters per second. Alouette River at Haney is one of the gauges that's within Maple Ridge, and it observed a peak flow of 131 cubic meters per second. Just a little bit after our dam release due to some travel time. So there was also a significant amount of local inflows that occurred in the city of Maple Ridge during this event. And this dashed blue line shows the bankful conditions along the South Alouette River. So they were exceeded, but only a little bit of localized flooding and no widespread flooding was observed in the city. The attenuation of the peak hourly inflows was observed at all of our lower mainland facilities, where we saw significantly high peak hourly inflows, but our peak dam releases were substantially lower. All of these peak hourly inflows were well below the design inflow events for all of our facilities. So there were no dam safety concerns with this event. The peak downstream river flows are also shown here and measured at different Water Survey of Canada reservoir gauges. And if we look at Coquitlam, it measured a peak hourly flow of 202 cubic meters per second, but BC Hydro's release during this time was 1 cubic meters per second. So you can see that there's also a significant local inflow that occurred downstream of our dam. So a number of flood alerts were triggered during this event, but all of the peaks of the river flows were attenuated by our reservoir operations.
Okay, so that leaves us on our conclusion slide. I'm not going to go through all these points, but the main one is that The November 14th, 15th event was well managed from an operations perspective at BC Hydro, but extreme events test our systems, and there are plenty of learnings, and those are included here. So I'll leave this up as we take questions, if we have extra time for questions, that is.
Great. Thank you so much, Tim and the team at BC Hydro. We're going to actually we're a little bit behind schedule, so we're going to go right into the next talk. So Alyssa Stevens is a senior operational meteorologist at Environment and Climate Change Canada. And while they are putting their slides on, just a note too, we will be taking the questions from the chat. So do put your questions in the chat and we'll try to get them to the right folks.
Thanks, Ashley. Everyone can hear me and my screen is showing full screen, hopefully.
Can confirm both. Thank you.
Perfect. Okay, so thank you. So yeah, like she said, like Ashley said, my name is Alyssa Steves, and Dragana Kornick and I put together this presentation initially in November, December, and it's been modified for the talk today. So I'll just kind of highlight, I work at the Canadian Meteorological Center. Oh, we're not going to play. There we go. Sorry. I work at the Canadian Meteorological, or what was formerly known as the Canadian Meteorological Center, and now the Canadian Centre for Meteorological and Environmental Prediction with A&P. So today I'll be talking about actions, analysis and prognosis that unit took in advance of the mid-November atmospheric river that affected southwestern BC, as well as some findings during the subjective model verification process in terms of lead time, precipitation amounts, and precipitation distribution. And these actions before and after the system reflect highlighted points of the A&P mandate there. So I'll start by talking about some activities we did in advance of the event. We're going to go back to Monday, November 8th. We were doing a national briefing to that was this in particular. This was to the western half of the country. So a lot of service meteorologists listen, like warning preparedness, etc. Listen to these briefings every week. So this was on the Monday, and basically at the time we were aware that there was a system coming, another atmospheric river, for the weekend of November 13, 14. Guidance generally was highlighting associated significant precipitation for coastal BC after, as I believe was mentioned, 2 preceding systems. I know we mentioned the one on the 11th and probably one, I think, back on the 9th during the week. But for this system in particular, there was significant divergence amongst guidance solutions. So it wasn't really yet possible to determine significant impacts with much certainty. So those are a few slides that were included in the briefing. And the bottom line message was like, there is another, kind of atmospheric river precip loaded Pacific system forecast for the weekend at the time. But that does beg the question, how long before the event did the Canadian guidance start showing the severity? And it seems the answer in the grand sense was about 3 days. So I'm going to show a couple of products. One's from our global ensemble. I apologize in advance for the Zoom, and the global deterministic on the right. So the product on the left is rainfall threat. Both of them are covering 24-hour period from 0Z November 14th to 0Z November 15th, basically November 14th in Zulu time. That basically was the height of when the most precipitation would have fallen during the event. So the ensemble product, just to mention, the red there highlights where 60% of the ensemble members suggest at least 50 millimeters in the 24-hour period. And then with the deterministic on the right, it's just straight up 24-hour precipitation. So red in that case is where the model is exceeding 150 millimeters in 24 hours. So it's a quick loop just showing 3 runs from 12Z November 9th through 12Z November 10th. So you can sort of see it goes from, there's going to be more precipitation. And then by that last image, it's like, okay, there are signs that there's something pretty significant coming. Between the ensemble threat and the deterministic output, the areas were not really in line yet. But 24 hours later, so by the 12Z November 11th run, the deterministic there on the right has shifted its maximum precipitation area further south. And it's kind of in line with where the ensemble is highlighting its greatest rainfall threat over southern coastal BC. So at this point, it's Thursday. That's when we would produce our, what we call the Vigilance Bulletin, has a more formal name. It basically is supposed to highlight weather-based impacts across the country day by day, I think days 3 to 7. So the day 4 was November 14th. And at that point, we had highlighted a rare, severe impact or orange threat. And not shown, but the days before and after for the same, atmospheric river highlighted yellow threat, referring to the whole system. And each little area of color does get a little bit of a discussion associated. So in this case, there was references made to significant amounts of runoff, already saturated or impermeable surfaces, landslides, and snow making travel difficult. And I mean, Bobby went over that quite well, talking about, the ground being saturated from the earlier cases. There were burn scars, etc. So we, that despite the fact that it was a day 4, we highlighted that orange threat. So moving on, so every night we do these significant weather discussions. So for that one, it would have been based on the following set of guidance zeros at November 12th. So we continue to suggest a significant event for the weekend. So the lower right image there is more global ensemble output. It's covering a 3-day window from the 12th to the 12th to the 14th. Just highlighting the threat areas according to the ensemble, again showing rain, runoff, snowfall, rain, freezing rain, for example. And there was also reference made to an ECMWF product showing atmospheric, an ensemble atmospheric river forecast. So the orange column there is the weekend event. The green one's actually the November 11th event. And it's showing on the atmospheric river scale, showing a 4 out of 5. It's fairly significant. And that the location chosen here actually was southwestern Vancouver Island, which, as we know, was also pretty well impacted by this event. So this would have been issued early that morning, and then we had our morning meeting around 8:30. And so we were discussing these products and, the amount of impact we're starting to suspect is coming. So the EMP chief actually then reached out to the Pacific Storm Prediction Center to highlight the severity of what we're, kind of giving him a heads up on what we're seeing. At this point, it is the 12th. The event did start on the 13th. So I won't get into this. This is the same map that Bobby showed in his presentation. Again, it's an it's model data with interpolation from radar and gauge amounts, showing the kind of the distribution of precipitation over the 3-day period. That one in particular is from 12Z on November 13th to 12Z on the 16th. And then there's the special weather summary with specific observations. And again, Hope is circled there with the 295. Total being the highest observed amount that they included in the special weather summary. But in any case, I mean, there are tons of observations exceeding 100 millimeters and a few exceeding 200 millimeters. That was the total between the 13th and 15th. So going into the verification, I'll start with the ensembles. So starting with the probability of exceedance for the 72-hour window, I did 0Z on the 13th to 0Z on the 16th. So a 3-day window. So start with the global ensemble. And this is just basically the final run that would have covered the window. So 0Z November 13th. So, you can see from that, it has no problem highlighting, very, very pretty much guaranteed all the members say you're going to exceed 100 millimeters, at least around the Fraser Valley, lower mainland kind of areas almost. And not so much, further up the coast, central coast, Western Vancouver Island, it's maxing out at about 50 to 60% exceeding 100. Moving on to 150, like likelihood of exceeding 150, it's maxing out around 50 to 60% just north of Abbotsford and the terrain there. That's just north of the Fraser Valley. And then the image on the right, non-zero, but very low likelihood of exceeding 200 millimeters it's centered around the Fraser Valley, mind you, but very low probability. If we can look at our regional ensemble, it's a lot better. It has take advantage of the higher resolution, so has a much larger, further north distribution and much more detail showing where it's very likely to exceed 100 millimeters, even 150 to 200. What I noticed here is, it's hard to see, but there's a little notch near in the southern end, and it is extending the 150 millimeter likelihood into Hope. It doesn't do that for the 200 millimeter, unfortunately. So better performance, certainly compared to the global ensemble, but still not really capturing the full the maximum impact of the event, and at least over certain locations, certain critical locations. And that's as late as we could do. Like, you couldn't have a lower run to capture the window. And then just, not really good for forecasting, but in terms of like getting an idea of what the extremes are going to be, I looked at the 100th percentile again for that same 72-hour window, and I have 0Z runs from the November 8th right through again November 13th. So it sort of starts out as, again, the global ensemble. It starts out being too spread out. So like, it's just there are members saying, like, the highest amounts could actually end up being further north, anywhere from further north to further south. But over time, as you might expect from an ensemble, it did reduce that maximum precipitation area while keeping the higher values over the Fraser Valley. And then with successive runs, it continued to concentrate and increase the maximum precip value around the Fraser Valley. And finally, with the last run, amounts exceeding 280 millimeters concentrated near the correct area, including Hope, with an ensemble maximum of 322 millimeters. And again, that would have been the terrain, I think, north of Abbotsford. And again, we can't, the regional ensemble is only 72 hours long. So for 72-hour window, you're only going to get output from one run. So that was the regional ensemble distribution. It does have Hope in that maximum area. The 100th percentile was saying, yes, Hope could see amounts in excess of 280 millimeters of precipitation. And there's an ensemble maximum, again, north of Abbotsford, of 588 millimeters. And then looking at the deterministic precipitation, something I found interesting, and it kind of goes with what Tim was talking about, actually. There was sort of a critical change in the regional and high resolution models, so 10 kilometers and 2.5 kilometer resolution grid spacing, between their forecast from 0Z November 13th to their forecast from 0Z November 14th. And again, this is not a 3-day window. This is for the 1-day window, 0Z November 14th to 0Z November 15th. So just think November 14th, 24-hour. I say it's critical because this is the guidance that would have been available when the initial public rainfall warnings were issued on November 13th. So this is what the regional deterministic, for example, would have been saying at the time. It's got basically all the heavy precipitation. It's got precipitation to the south, yes, but the heaviest amounts are basically north of the Fraser Valley only. And then 24 hours later, for the same window, so it's basically a nowcast, it starts at 0Z November 14th. The 0Z November 14th run, there's a shift in the distribution. You can see all the precipitation, it has shifted further south. That's pretty critical because now you have heavy precipitation affecting both sides of the Fraser Valley, and much higher precipitation around or across the border, which affected the Nooksack River in Washington State. And as Bobby mentioned, when the Nooksack floods, it impacts the Sumas Lake Basin in Abbotsford. So that's that there. So that's a critical difference in the distribution. I took a look at that same RDPS, the regional deterministic. I subjectively verified it against its own analysis with time. So the blue shading shows where the forecast the forecast 500 millibar heights were too low compared to the analysis, and then yellows are vice versa. The forecast is not low enough. So early in the forecast, or even by 12 hours, you can see in this elongating trough in the Pacific, the RDPS starts being too deep with the southern end of the trough, and not deep enough with the leading edge of that upper trough further north. And this continues as the leading edge of the trough carrying the atmospheric river came into coastal BC. And you can, and again, this is the interesting thing where you can sort of see there's that anticyclonic effect that Kent was talking about, which was pretty interesting. So it was a little more pronounced in what actually happened compared to what was forecast, and I think what happened was things shifted further south. So I mentioned both the regional deterministic and the high res deterministic. So looking at the higher resolution deterministic, again, between the two different runs, 0Z13 versus 0Z14, you can see there was again, that happened again with the higher resolution guidance. It was still too far north in that older run compared to the newer run. So yes, it also had that problem. And then just for some specific precipitation verifications for like Vancouver, Abbotsford, and Hope, that older run was really not forecasting enough precipitation for these sites further, a little kind of on the southern end of the rainfall. For example, it was only just over 75% capturing the amount at Vancouver and Abbotsford, and only about 50% for Hope. So really significant differences, and we're within 48 hours at this point, so it's a short range forecast. And then another thing I'll mention, we had a model upgrade on December 1st. So, of course, it was just half a month later, basically. And in the meantime, these new versions were running in parallel, and we were evaluating them. So, the question is, did this guidance handle the precipitation distribution better? So I have the same output from the operational, the old version, from 0Z November 13th. Now look at 0Z November 13th from its parallel equivalent, the newer run. And you can see it did a better job with the precipitation distribution, again, further south. So it was better. And then again, with the high resolution guidance, the 2.5 kilometer, there's the operational from 0Z November 13th. And then it's parallel equivalent from the same run. You can see again, it was distributed further south as well. So that's all I was going to cover in the time I have. So yeah, we had the system on our radar back on November 8th. The Canadian guidance, at least at the global scale, ramped up the threat between 12Z November 9th, 12Z November 10th. Initially, the deterministic was further north than where the ensemble was kind of saying the highest threat seemed to be, but it did catch up by November 11th. At that point, AMP was taking action, highlighting the orange threat on the visual loss, highlighting severe threats in the FXN discussion. That following evening, the AMP chief passed word on to PSPC. And then in terms of verification, again, our ensembles did, as I think Tim sort of alluded, our ensembles did not anticipate such extreme values for the storm. Again, the regional ensemble did a better job, but the observed amounts did not exceed the 100th percentile of either model, at least in terms of like the highest amount forecast. They weren't, I'll say they weren't co-located, but the highest amount forecast by the ensemble versus the highest amounts observed, there was not an exceedance there. And again, there was that critical last minute shift south in the higher resolution deterministic forecast between 0Z November 13th and 0Z November 14th runs with, fairly significant change to the level of impact, and the respective forecasts from the parallel guidance from the newer versions performed better. So I will stop there. Thank you.
Great. Thank you so much, Alyssa. That was really informative and wonderful. So we are a little bit behind time. In the interest of time, if you have questions, please put them in the chat. And Alyssa, if you're comfortable with answering them there, we'll go on to the next speaker. So we'll go on to Melinda Brugman. Dr. Melinda Brugman is a senior research and development meteorologist at the National Lab for Coastal and Mountain Meteorology at the Meteorologic Service of Canada. And with that, we will go on to Mindy's presentation.
Hello, I'm trying to get my presentation up for you. And what I can say is thank everyone so far for their terrific presentations. I hope I do justice to it. Sorry, we're just a little bit late, but we'll pull through here. Alyssa, your information your team sent to us was really critical. And this will give an example of how we used it. I was asked on the 12th, right after Remembrance Day holiday, that are we really going to have a severe storm? How well did our rating system work that we've been developing? So I'll try to show you. This is ECAR, Extratropical Cyclone Atmospheric River, a multivariate atmospheric river scale for Canada. We're working as a collaboration. Anyone's welcome to join us as well. but particularly with BGC Engineering, Matthias Jacob, and the River Forecast Center, and then many in our department. Let's just do a quick outline here. We'll look at the objectives, existing and experimental rivers, atmospheric river scales, and then we'll look at this same case. We'll get the predictions, observations, consequences. A lot of you want to know how well, what are we developing? How well does it work? And we think we have a really good product, but we've got more work to do, and it is experimental. Then we'll look at climate change effects on frequency and magnitude. Alex Cannon, a participant, has done work on. The objectives are to create an atmospheric river storm scale that's linked to specific damages. And we call it an experimental ECAR scale. And we're focusing on important things for Canada. And the atmospheric river scale is to be useful for public regulators, emergency response managers, and the media. It should be able to trigger the war room type of approach to say, hey, we got a big problem and we want to get people together on this. We have a prototype for the BC West Coast, but it actually can work for all of Canada, but we need to expand it to more regions with more help. Let's look at a number of the storms. Particularly, we want to get the worst storms, which we call 1 in 1,000-year storms, or even worse than that, our superstorms. And we want to identify them early, and we want to identify harmful incoming storms. So we want to make sure the harmful ones are in our high categories. And we want to look at the effects of climate change, and we want to move to gridded, of course, immediately, but we'll only do it when we believe it's it's accurate. Let's look at some of the scales. Not everyone's aware of what has been done and described well in Ralph et al. In BAMS 2019. This is the atmospheric river scale used by CW3E and NOAA. Goes from 0 to 3 days and up to 1250 or more. And it's based on integrated vapor transport in the vertical, the maximum amount and the duration of the storm. And this works pretty well because most major storms, all of them, have a warm, moist jet. And this is used as a proxy to indicate storm severity. We have IVT and TIVT, which is a time integrated vertical integrated vapor transport. And for this, it's simple. We just figure the length of the storm and the maximum IVT. Now that we've gone beyond this in our scale, the further left column is the color scale we use. Then we are analyzing each storm in the standard way with IVT. So and we have our levels there. And when expanded, we just have anything above 1,000 is category 5 or more. But we also have durations. The standard scale only goes out to 3 days. And for these worst storms, they could last a week or more. And we'll try to show you why we think that these are a concern. We can just cap the scale at 5 and say anything beyond that is a superstorm. Now, we've gone over and looking at return periods. This return period for precipitation, but many users want to have return periods for whatever is their major effect in that area. It might be heavy snow, freezing rain, landslides, floods. But right now, we're going to show you an example with precipitation. About 100 to 300 year storm would be category 5. But as we go up, there are these terms called probable maximum precipitation. And then the Gumbel distribution of precipitation, or any OBS, way out here in the tail, they have this term called probable maximum precipitation. Now, it's estimated different ways, but with the Gumbel distribution, we can show that it's about 3 times the 100-year event is a reasonable estimate for the PMP. Now, some use it aerial extent, but we're just looking at points here. If you look at the global warming projections, many of them are coming out with for about 3 degrees, about 6 times the 100-year event. So this is a straightforward, doable operational way we can give an estimate of storm severity that can help in our discussions. Then what we move from there is, what are the consequences? This Matthias Jacob has has used his expertise to help us on the South Coast. But the aim is to do this throughout British Columbia and throughout Canada for people. But to start with, rating 0 would be minor flooding, going all the way up to category 5, very long duration, and all of these catastrophic things. We've also seen atmospheric rivers are associated sometimes with severe thunderstorms, swarms, tornadoes, derechoes. You can look and you can see an atmospheric river could be related to them. But we're looking at precipitation mainly in flood and landslide events. This is Alyssa, this is the information. I took the rating, I read out this information, and this is what I sent on the day before the storm. And I'll try to show you how we did this. But why was the flooding so bad? For those not familiar with the area, you can see here's the Sumas Graben, and the Fraser River normally flows over here. But what happened in that is a Nooksack jumped the border, and as it does naturally, and it flowed and caused more problems, and it flooded all around. But there was flooding problems everywhere. There was, thanks to Guardian Graphic here, there's problems all around the area, which we've been talking about. Now, this is some of our new guidance. What changed my decision was seeing how our best high resolution model and our weather on the grid data was coming in very strongly with exceptional forecasts. And this is, for example, 24-hour total precip on the 2.5 kilometer model. This is the older P3 hydrometer scheme. For this, it's great because hydrometer drift is allowed, so it has more accurate distribution of precipitation. Then we had the snow here. Now this snow is calculated using weather on the grid with our newest snow level that is post-process. So we take diabatic cooling of the precip amounts and we recalculate the precip type. So this is one of our newest products, and I thought it worked quite well. They put out a snowfall warning here, but we knew this was coming. If you look at our 1 kilometer model, it was even better. It's not perfect, but it was amazing in the features it could show of the interaction of very heavy precipitation, very heavy locally along the Fraser Valley, very warm temperatures up to +10 in the valleys. Realizes we had snow and then it warmed and then it got very windy. Now here I'm going to show you some of the model differences. This is the 1 hour precipitation, and we're comparing the new IC3 model, came out in December, with the old P3 model. For example, here the precipitation, the green is the old model, and you can see that it hung on longer with higher precipitation, whereas the new model, boom, it stopped. So every model has its differences depending upon the terrain. So we have to always examine the model biases, as everyone knows. Even though the high res was very good, we know there are model biases. But look here, it had snow accumulated with cold temperatures, and then it warmed up rapidly. So this is a double, triple whammy of snow melt, which we could see. We had snow melt and about 10 centimeters, but then overall it lost 18 centimeters. So we lost snow that was actually there. And that just to show you the differences, a 2-day precip was 196 with the IC3. The old one was 220. And the observed was 252 at this spot. It was about 300 at Hope, as people have already seen. But I just want to highlight our new snow level product. It showed that we were well above 2,000 meters, 3,000 meter snow level when this came through. So it was a huge snow melt event. And looking at the intensity, duration, frequency, it was a 100-year event for the 2 days. So it was really significant. This is an example of our product. We have multiple ways to look it up, but this takes the high-res data, calculates the return periods, and we overlay it over the atmospheric river computed from the global model. So it gives you a really good idea what's going on here. So we knew there was very high level, a superstorm forecast for the South Coast, But look at Revelstoke, it was very high as well. But the situation there was the snow level was very low at 600 meters. So it did not realize the disasters that could have happened, but we are including snow melt, and because it's very critical. And the total Kappa precipitation, and this is a mix of model and observations and radar, because we don't have that much radar, but it did show that we were up in the order of 300 millimeters. But huge amounts of precip. We've seen this before. We just added in the Coquihalla, which was also a 100-year return interval. So it was a tremendous event, and the OBS did agree with what we'd seen. This is the river forecast, and it also came up about 100-year return interval. But just the caution is many of these rivers overflowed, and the ratings are of a great concern. So it was really good for Frank to talk about additional stream discharge and waste, because we need a lot more work to get these accurate in catastrophic events. Caution about return periods for these. So thanks to Alex Cannon, he cranked through all around for us. I call these my bubble bath warming plots. This is Japanese reanalysis going out to 10 days and 1980 to 2020, just to see whether we're somewhat on track. And he cranked out all these ensembles. Here's an example, 1950 to 2100. And it goes, and I'm just picking one that looked good, 0 to 10 days. You can see we're right about here, and we bubble along with a few catastrophic storms, and then we're increasing to the, we're on the cusp of a huge increase. So our conclusions are the rating is valuable for ECAR, and we're working with different stakeholders to make sure we have the most important impacts. We need this to help not only operations forecast better and to analyze our models, but also that we communicate the worst storms. We're adapting a classification from Ralph, but we're using automated return periods and weighted rating based on risk priorities. There's a predicted increase in the intensity and magnitude of these major storms coming in, and many existing infrastructures that are designed for assumption of stationarity can be threatened. And our scale is based on 1 to 3 days, but 5 levels, but we further classified using weather impact return periods and the seeding conditions. We didn't talk about that, but we now have programmed in 30 days. We're discussing others, preconditioning and regional sensitivities. And we could go out to 10 days or as long as people want. We have a 5, anything above 5 is catastrophic, but to help emergency managers and others, we can give out to 8 levels. And so there we go. Thanks.
Great, thank you so much, Mindy. That was really a wonderful talk. And my apologies to everybody for we're a little bit over time. So with that, if there's any last questions, if people could put them in the chat, but given that we are a bit over time, I apologize for that. We will wrap it up here and just thank, first of all, the speakers again for a round of really wonderful talks. This was a great session. Thank you also to Richard for being the technical support for this, and look forward to seeing everybody in the next session in this afternoon, as well as tomorrow, related to BC extreme events. So again, I think we'll end the kind of this talk or this part, but the chat will still be open if there's some questions. Thanks again, everybody.
Thank you to everyone.